All right, so here we have the temperature of coffee in a cup at time t minutes. It's modeled by a decreasing differentiable function, C, where C of t is measured in degrees Celsius for t between 0 and 12. Here are some of the values shown in this table. All right, part A. Approximate C prime of 5 using the average rate of change of C over the interval 3 to 7. Show the work that leads to your answer and include units of measure. This is simple if you know math or calculus. This is basically just finding the slope of C at 5 or the rate of change. Now we don't have 5 as a t value. So then what we do is we approximate it by taking the difference in the t's under the c's of t's. Well, that was kind of a weird way of saying it, but rate of change. So what we're going to do is we're going to take C of 5 or C prime of 5. It's approximately C of 7 minus C of 3 over 7 minus 3, which is 69 minus 85 over 4, which will be negative 16 over 4, or negative 4 degrees Celsius per minute. Don't squeeze it in there. Well, I mean, I guess you already did the test, so you don't have to worry about, listening to my advice on how to squeeze the problem in there. But yeah, here's your answer for that. Let me grab some scratch paper to kind of not cram the rest of the stuff on the paper. All right, use a left Riemann sum with 3 subintervals indicated by the table and by the data in the table to approximate the value of the integral from 0 to 12 of C of t dt. Interpret the meaning of the integral 1/12 times the integral from 0 to 12 of C of t dt in the context of the problem. Oh, okay, so this is like a two-part thing. I don't know why they did that, but anyways, so let's just find this first thing. So 0 to 12 of C of t dt using a right Riemann sum, or I mean using a left Riemann sum, we're going to use the three values here for these 3 rectangles. So the first rectangle is going to have a width of 3. So it's going to be 3 times 100 plus the second rectangle is going to have a width of 4. So plus 4 times 85 plus 5 times 69. Doing the calculator math, you will get 985. Now, when it says interpret 1/12 of this, so 1/12 times the integral of 0 to from 0 to 12 of C of t dt. This is going to be 985 divided by 12, or about 82.083 repeating. This is basically saying that the average temperature from 0 to 12 minutes was about 82.08 degrees Celsius. And part C, the rate of change of the temperature of the coffee is modeled by C prime of t equal to this. where C prime of T is measured in degrees Celsius per minute. Find the temperature of the coffee at time T equals 20. Show the setup for your calculations. Okay, so okay, so what we want to do is just take the temperature at 12 and then add it to this times 8. Another way to think of this is let me show you. When we can do this with a calculator, but remember that or understand that the temperature is changing by this much on average per after 12 minutes, or from 12 to 8 from 12 to 20 minutes. So actually I kind of said that wrong. We want to have the integral from 12 to 20 of this and then add it to the temperature at 12. So add it to 55. So I could probably fit it right here. Yeah. So C of 20 will be approximately the temperature at time 12 minutes. So 55 plus the integral from 12 to 20 of this whole thing. So we can use our calculator. What we're going to have here is negative 24.55 e to the 0.01 x all over x negative 20.4. Whoa, negative point will almost screw that up. Oof. Negative 0.2455 e 0.0. Can't see that 0.01 x. I really screwed this all up. Let me 3 times 100 minus. No, that's never mind. Oh my god. Sorry guys. Having a long day. I didn't screw that up. I was mixing it with the one right below, which is that's what I do sometimes. Okay, so I think we're good. Okay, that will be what we will add to the 55. So it's plus 55. Which will give us about 40.33 degrees Celsius. Okay. All right. The last part for the model defined in part C can be shown that the second derivative of C is this for T between 12 and 20. Determine whether the temperature of the coffee is changing at a decreasing rate or at an increasing rate. Give a reason for your answer. Okay, so let's just graph this. Menu, graph, function. On top, we're going to have 0.2455 e to the 0.01 x times 100 minus x. This whole thing will be divided by x squared. Here we go. Damn, look at that thing. Zoom out of this. Zoom out. Center. Yeah, sure. Okay, so it's doing some like hyperbola action. Um, but it's essentially decreasing, but it's concave up. But as you can see, it's still, since the second derivative is positive. Now that means that the first derivative is going to be increasing, but it's just increasing very, very slowly. It's increasing the rate at which it's increasing is decreasing. It's very confusing. So it's always increasing, but it's just increasing by a less amount. So maybe like, for example, maybe you like the first minute it's increasing by 1 degree per minute. Then the next minute it's increasing by half a degree per minute. It's still always increasing, but it's increasing at a decreasing rate. That is really weird to say. But we're talking about we're just talking about the temperature. It's changing at oh yeah, it's at an increasing rate. We only care about the temperature increasing rate since C double prime. This is a weirdly worded question, and I don't know if they're trying to test your grammar skills, but yeah, the temperature of the coffee is changing at an increasing rate since the second derivative is positive. Okay, so there you go. Hope that helps. Let me know if you have any comments, or let me know if you have any questions by leaving a comment. And I'll try to get back to you, and stay tuned for the next video. I'll see you guys then.